From the design of a bridge in Tokyo to building a car in Detroit or even smartphones assembled in Shenzhen, they all come to life with so much precision and universality. Despite the diverse languages, cultures and traditions of the people behind these marvels, there's one universal language that brings their ideas to life: engineering graphics. From simple sketches to intricate blueprints, technical drawings transcend barriers of spoken language. In today's video, we'll explore the incredible role that engineering graphics play in shaping the world around us, exploring the different types, understanding better why they are the universal language of design and innovation. Engineering graphics serve three essential purposes in the design process: visualization, communication, and documentation. First, there is the sketch. These quick freehand drawings capture the raw idea during the ideation stage. They are simple, they are spontaneous, and vital for documenting creative thoughts in their earliest form. I like to think of sketches as the seed of innovation. They provide just enough detail to inspire and communicate concepts within a team. Unlike computer-aided designs or detailed drawings, sketches can be created and modified quickly. This makes it easy to experiment with multiple variations of a design without investing significant time or resources. Sketches can thus allow for small incremental changes to a concept. Designers can tweak proportions, shapes, or layouts and compare different options side by side to determine the most effective solution. Once an idea takes shape, it's time for a more sophisticated way of visualizing it. This is where 3D models come into play. These detailed digital representations help visualize the product from every angle, making it easier to analyze and improve the design. They allow designers to test the functionality, fit, and form of the product, ensuring it meets performance expectations before moving forward. These models store vast amounts of design information, including dimensions, materials, and geometry, which can be modified easily. 3D CAD design combines descriptive and analytic modeling qualities, provide a holistic representation of the final product. Descriptive qualities ensure the model accurately depicts geometry, material, and assembly, while analytical features allow predictions of real-world behavior. Some key 3D modeling approaches include the wireframe modeling. Wireframe models represent objects through lines and curves, forming the basic skeletal structure. While simple and cost-effective for basic shapes, they lack detail in volume and surface data, making them less useful for complex designs. Next, we have surface models. Surface models define only the outer layer of an object, resembling an empty box with no internal structure. These models are ideal for industrial designers focusing on aesthetics and product styling, often incorporating rendering tools to create photorealistic visuals. Next, we have solid models. Solid models include detailed volume data, making them indispensable for engineering analysis and simulations. They store comprehensive information such as mass, center of gravity, and moments of inertia, facilitating precise calculations. And lastly, we have the constraint-based parametric modeling. This method introduces relationships and constraints, allowing designers to adjust one feature while automatically updating dependent ones. Such flexibility is crucial for iterative designs where frequent modifications are expected. As a little addition, advancements in CAD softwares now include virtual reality integration, enhancing the design process even further. Virtual prototypes enable users to interact with a 3D model in an immersive environment, offering insights comparable to those from physical prototypes. As the design process advances, precision becomes paramount. Detailed 2D drawings provide the exact specifications needed for manufacturing and assembly. These drawings eliminate ambiguity, ensuring every part is provided and assembled exactly as intended. Creating 2D drawings is a key part of the design process as they allow for clear communication of a part's design intent and manufacturing details. The art of producing these drawings lies in presenting information that is easy to interpret, ensuring the dimensions, views, and lines are placed logically to help the reader understand both the part and its intended use. As far as details go for 2D drawings, the field of engineering graphics is shaped by a commitment to uniformity and precision, essential for ensuring effective communication across industry, manufacturing, and science. These principles are upheld by standards set forth by prominent organizations such as the American National Standard Institute, the American Society of Mechanical Engineers, and the International Organization for Standardization. In addition to respecting these norms while preparing 2D technical drawings, dimensioning, tolerancing, and surface finishing are vital components of engineering drawings as well, providing the necessary information to manufacture and assemble a part with precision. These elements ensure that the design intent is accurately interpreted and that the part meets the required functional and aesthetic standards. Dimensioning is simply the practice of adding measurements to a drawing, indicating the size and location of features on a part. Tolerance, on the other hand, is the practice of specifying the permissible limits or variations in a part's dimension. Since no manufacturing process can create perfectly dimensioned parts, tolerance defines the acceptable range of measurements, ensuring that parts fit together and function as intended. Properly dimensioned and tolerance drawings with clear surface finish details and other critical instructions make it possible for manufacturers and assembly teams to produce high quality parts efficiently without ambiguity or errors. These details bridge the gap between design and physical production, ensuring that the designer's vision is accurately realized. Engineering graphics embody a universal language that unites engineers, designers, and machinists worldwide. From the earliest sketches that spark innovation to the 3D models that refine ideas and precise 2D drawings that bring them to life. These tools transform abstract concepts into tangible realities. They break down the barriers of language, culture, and geography, enabling seamless collaboration and driving progress on a global scale. Thank you for watching, and I'll see you all in the next one. Bye-bye.